Hi, my name is Scott Simpson, and today we'll be talking about isotopes, how to determine the number of protons, neutrons, and electrons in an atom. So we know the current model of the atom. It looks like where we have a nucleus, and we have a probability electron density that's smeared around that nucleus. So we can't say exactly where the electron is, but we can say a probable location of this electron. And this is due to the Heisenberg uncertainty principle and several other things in quantum mechanics, which we'll talk about later. Till we get to that point, let's discuss atomic number, mass number, and isotopes. So these are descriptors we use to describe different elements and atoms and ions that make up all of matter. In this case, the atomic number, we're going to give that the symbol Z. And what this is it's the way that the periodic table is numbered. What you're actually keeping track of is the number of protons. So this is equivalent to the number of protons. And we know that this is how the periodic table is numbered, starting from 1 and going on down. The mass number is another important point. We're going to give that the symbol A. And what this is it's the number of protons plus the number of neutrons, essentially. Number of neutrons. We don't incorporate the electrons in here because the electron's mass is so much smaller by several factors compared to the mass of the proton or the neutrons. So we just leave them out for now. Okay, so on the periodic table, you'll notice a lot of times that the mass number, or excuse me, the atomic number is above while the mass number is below. We're actually going to do the opposite. The reason for this is we want to indicate that there is a difference. What you see on the periodic table is for a large ensemble, or 6.022 times 10 to the 23rd atoms, and it's a relative or a weighted average for the mass number. In this case, we're talking about specifically one individual atom. So in this case, what we would have is we would indicate the mass number up top, and we would have the atomic number in the bottom left, with our element symbol right here. So this is our mass number. And this Z down here, call it, is our atomic number. From that we can figure out how many protons and neutrons are in a system. So let's consider an example. So, question, how many protons and neutrons are in O16? Okay. So, we have oxygen. We know its atomic number. Its atomic number is right down here. Its mass number, 16, is up top. So we already know the number of protons quite easily by just looking at the mass number. So number of protons, we're going to shorten that to P plus, is equal to 8. But what about the neutrons? Well, to figure that out, number of neutrons, all we have to do is subtract off. We take our mass number, subtract off the number of protons that we have, because we know the mass number is a combination of the protons and neutrons, and from that we should get number of neutrons. We're going to put n sub 0, or n naught or n0 up top. So we can do that. Number of neutrons is equal to 16 minus 8, which is equal to 8. Now, in this case, the number of protons and number of neutrons were equivalent to one another. That doesn't always happen. So don't just assume that because it worked out in this case, it's going to work out similarly for other cases. So now, let's figure out about the number of electrons. So right here we had a neutral system. What happens when we have a charged system or an ionized system? So let's talk about the number of electrons. Because electrons are actually a huge deal when it comes to chemistry. Even though they're really small, a simple jump or change of them mean a big consequence. So number of electrons. And this is determined by the charge on the molecule, or excuse me, on the atom, and the number of protons that are in the system. So determined by number of protons and charge, total charge on the system. An important point is a neutral species, a neutral atom, has equivalent number of protons and neutrons. A neutral atom has an equal number of protons, we're going to put P plus, and electrons. We're shortening electrons to E minus. Okay. So for example, our previous example, if we went back to our oxygen, C16C8, the charge is typically indicated over here. So if we were looking generically, we would have X, we would have that mass number up top, we'd have that atomic number in the bottom left, and then we would have Q, the overall charge. In this case, nothing's written there, so that insinuates that we have a 0 there. Since we have previously discussed that the number in a neutral system, one that has a charge of 0, the number of protons would be equal to the number of electrons. The number of protons is equal to number of electrons in this system, which we can easily look and see, okay, that's 8. But what about for a charged species? Let's consider O2 minus. What about then? Okay, we have an overall net charge. Since we have an overall net charge, that means there are more negative particles than there are positive particles. Neutrons, they don't add anything, their charge is net 0. Electrons have a -1 charge where protons have a +1 charge. So keeping this in mind, we have an overall -2 charge, which means we have more electrons than we have protons. So, to figure this out, we have to look at the difference between the two. We know our number of protons is equal to 16. And we also know number of protons plus number of electrons has to equal -2. Let's manipulate this equation around. Let's try and solve for number of electrons. So if we do that, oh, I'm sorry, this shouldn't be a plus here. This should be a minus. There we go. So let's manipulate that through. We're going to move this one over to the other side. So we got number of protons is equal to number of electrons -2. Let's move that -2 over. We end up with number of protons plus 2 is equal to number of electrons. The nice thing is we know the number of protons. That number is 8. We have to add our 2. Therefore, our number of electrons in this system is 10. Let's look at another example. That was a positively charged species, or excuse me, negatively charged species. Let's look at a positively charged species. So in this case, let's consider calcium 2 plus. Okay, and we have to figure out the number of protons, neutrons, and electrons in this system. Again, number of protons is simple. All we have to do is look at that atomic number, which is 20. We have our protons. Number of neutrons. That's going to be equal to our mass number minus our atomic number, because those are the only two particles that contribute to the mass for the most part. So we'd have 40 minus 20, and then back up at 20. Again, coincidence that it works out this way. Now we have to consider number of electrons. So we have number of protons, which are all positively charged, minus number of electrons gets us to our charge. Okay. Since this species is overall positively charged, that means there are going to be more positively charged particles than negatively charged particles, which means our number of protons should be greater than our number of electrons. Okay, when we plug in and when we solve, we have to end up with positive 2. We know that this is 20, this is some unknown number, and this is 2. When you solve for this, you find that the number of electrons is equal to 18. Okay. So, I said we were also going to discuss isotopes. We figured out the atomic number, mass number, number of electrons, but what about isotopes? How do isotopes differ here? So isotopes, they are of the same element type and the same atomic number, but their mass numbers are different. A common spot where this is seen is through carbon or hydrogen. So isotopes. Let's first write down that definition. Isotopes, they're atoms with the same atomic number, but they have different mass numbers. So an example, we'll first look at hydrogen, H1, call that one hydrogen, hydrogen. If we add, so this system has no neutrons in it, looking at the atomic number and mass number. Remember that mass number is number of protons plus number of neutrons. We already have a 1 here, so that means if we go to add that to the number of neutrons or subtract it to figure out number of neutrons, we end up with a 0. If we plunk one more neutron in, we end up with deuterium. Ooh, except I can't spell it. There we go. Deuterium. There we go. When we get to deuterium, this is actually a very important isotope. In organic chemistry, it's used a lot of times to look at different mechanisms to see how things occur. It's quite interesting. And then we have tritium. And if you look at the relative abundance of each of these, they have different relative abundances, which we'll talk about in another video later on. But hydrogen is the most abundant, followed by deuterium, followed by tritium. So really the important point between isotopes is that they are atoms with the same atomic number, but they have different mass numbers. Okay. So if you have any questions, please leave me comments below, and have an awesome day. Thank you.